So here you see beta is equal to IC by IB, and you have the expression alpha is equal to IC by IE. Substituting these in IE is equal to IB plus IC, you get these expressions in terms of alpha and beta. And alpha you can finally derive as alpha equal to beta by beta plus 1, and beta is equal to alpha by 1 minus alpha. Also, you can recall this expression ICEO equal to ICBO by 1 minus alpha, and but using this equivalence 1 by 1 minus alpha is equal to beta plus 1. From so what will you get finally? ICEO will be approximately equal to beta times ICBO. Beta is very large value, very much greater than 1. Also, IC equal to beta IB, and IE is equal to IB plus IC. So this IC, if you replace with beta IB, you get an expression for IE in terms of IB and beta. Okay, beta is actually relating IC and IB, but you get an expression for IE as well. Now, before proceeding to common collector configuration, let us compare the dynamic resistances of common base and common emitter. So dynamic resistance in the sense input dynamic resistance and output dynamic resistance. So for common base, if you write down the expression, the input dynamic resistance is given by for delta VEB by delta IE, the change in input voltage by change in input current for constant output voltage. And for common emitter, it is Ri is equal to delta VBE divided by delta IB. So what can you conclude from these expressions? This is in milliampere range and this is in microampere range, which means the input resistance for common base configuration is much lower than that for common emitter configuration. This is in microampere range. Okay, if I specifically give you the range of values here, this for common base configuration, input dynamic resistance will be in the range of 20 ohm, and for common emitter configuration it will be around 1 kilo ohm. Okay, then if you want to find out the output dynamic resistance, what is the expression? It is given by delta VCB, the output voltage by output current for constant input current. For common emitter configuration, it is RO equal to delta times VCE divided by delta times IC, the output voltage by output current for constant input current, which is IB. IB equal to a constant. Okay. So in this case, you know that the output characteristics of a common base configuration, if you observe, it is almost horizontal. IC is equal to IE, it is following IE, and it is almost horizontal. Whereas here, for common emitter configuration, it is increasing with VCE. It is not a horizontal line there. Okay, so what can you conclude here? Here there is no change in the collector current for a given variation in collector to base voltage, which means the output resistance is very high since delta AC is very small for a certain value of delta VCB. Now here it is not horizontal, and as we increase VCE, the collector current is also increasing by an appreciable amount here. So which means the output dynamic resistance is not very high. It is of the order of 10 kilo ohm here, and it is of the order of 1 mega ohm here. It is very high for common base configuration. So what can you conclude here? The input dynamic resistance for common base is very low. The output dynamic resistance of common base is very high. Whereas for common emitter, you can see that it is in the medium range. Input dynamic resistance is low and output dynamic resistance is high. Okay. Now, common collector configuration, it is not used in amplifier mode because of some of the characteristics of this common collector configuration. We are not going into the detailed characteristics, but just understand the connection here. The collector is common here, and this is a PNP and this is an NPN transistor which is used. Now, for about the current amplification factor, we will just go through. The current amplification factor is the ratio of output current to input current. So, it is delta IE by delta IB. Gamma is a notation. And if you want to find a relation between gamma and alpha, gamma is delta IE by delta IB. And alpha is the current gain in common base configuration. So, it is delta IC by delta IE. There's a mistake here. And you can find an expression for delta IB and delta IE and delta IC in terms of delta IE and delta IC from your basic IE is equal to IB plus IC equation. Now gamma, if you want to find out, it is delta IE by delta IE by delta IB. So delta IB is delta E minus delta IC, and you can divide throughout by delta IE. You get an expression, final expression, that is 1 by 1 minus delta IC by delta IE. This is nothing but alpha, or gamma is equal to 1 by 1 minus alpha. So the above relation shows that the value of gamma is nearly equal to beta. That is, the current gain of this is similar to our common emitter configuration. The input resistance is very high and output resistance is very low for common collector configuration. It is just opposite to common base. It is, input resistance is very high and output resistance is very low. The voltage gain is very low, and this circuit arrangement is mainly used for impedance matching. Now the comparison of the configurations, if you see, these are the common input terminals, then common terminals between input and output. Then these are the input currents, output currents in these three configurations. Current gain is less than 1 and close to 1 for common base. Beta current gain for common collector and for common emitter. These configurations are current gain values are high, and input voltage for common base is VEB, for common emitter it is VBE, and common collector it is VBC. Output voltage notations we have marked with respect to the common terminals. Now the voltage gain is medium for common base configuration and common emitter, and it is less than 1 for common collector configuration. The input resistance is, we have already discussed, very low and very high for output resistance is very high for common base, in the medium range for common emitter, and for common collector it is high. Input resistance is high and output resistance is low. Now regarding this voltage gain, if you want to want me to explain, I can explain it for the common base configuration for the time being for your understanding. So for common base, you can see, consider this PNP transistor. Okay. Now this is properly biased. We are just showing the, I am just showing you the input signal here, V in. Okay, this is common base, and this configuration I am taking the output across a load resistance RL. Okay, so this V in, if I take it as say 10 millivolt. Okay, and the input resistance, suppose it is 20 ohm Ri. Okay, of this common base configuration. So the output will be, the voltage across this RL will be V0 equal to I0 into RL. Whatever the output current, collector current we have, that I am taking it as I0. Okay, so at the input side, the input current will be, for this 10 millivolt peak AC signal I am talking about, the peak value. So for this 10 millivolt peak, the input current will be 10 millivolt by 20 ohm. Okay, so that will be 0.5 milliampere. Okay, so alpha is less than 1 or close to 1. I am taking alpha value equal to 1. Then what about the output current? The current gain is 1 I have taken. So output current will be same as this, and it will be 0.5 milliampere for common base. What about the voltage drop across RL? V naught will be I naught into RL, and that will be in the range. What is I naught? 5.5 milliampere, and that into RL, suppose it is 1 kilo ohm. Okay, you get it as 0.5 volt. Okay, so from 10 millivolt, what has happened here? From 10 millivolt, you got an output voltage of in the V range, that is 0.5 volt. So the voltage has got amplified here. The peak value of the input signal gets amplified here for the common base. There is a voltage, significant voltage gain here, but current gain is very low. Okay, but for common emitter in a similar manner, if you analyze, you will see there will be medium voltage gain and high current gain also. So there will be power gain for common emitter configuration. For common collector, it is voltage gain is less than 1. Now that is why this common base configuration is used in pre-amplifier circuits. These pre-amplifier circuits are given at the input of the main power amplifier circuit to amplify the voltage alone. So just to provide voltage gain, we can connect a pre-amplifier circuit. It won't offer any current gain. Then this common emitter is widely used in amplifier circuits, and common collector, because of its characteristic of high input impedance and low output impedance, it is used for impedance matching. Now let's see why common emitter configuration is widely used in amplifier circuits. Now let's see why a common emitter amplifier is widely used in amplifier circuits. So the main purpose of a transistor is to amplify weak signals, and for that you have to form the transistor amplifier circuits, which I for the time being represented as a block here. So in many cases one amplifier may not be sufficient. You need to cascade many amplifiers, okay, to amplify this weak signal. Now suppose this Vs is the signal that you want to amplify, and Rs is the source resistance. Okay, so this amplifier 1 should have some properties. As you know, this signal should reach the input of the amplifier 1. So this amplifier 1 should have these two terminals, the resistance should be very high. In order to avoid this, the signal is already a weak signal. In order to avoid it getting dropped across the source resistance, this value across this terminal A1, A2 should be very high, the resistance, which means the input resistance of the amplifier should be very high. The second point is that you are connecting amplifiers in cascade. So the second amplifier connection should not affect the performance of or disturb the performance of this first amplifier. For that, you should note one more thing. This amplifier is acting as a source to this amplifier, which means the resistance of this amplifier, the output resistance of this amplifier should be low, very low. And to this source you are connecting the second amplifier, isn't it? Which means this input resistance of this amplifier should be high again, and the output resistance of this amplifier should be low. And to these terminals, say I call it B1, B2, you're connecting the load and taking the output. So the amplified signal is taken as output across this load resistance RL. Excuse me. That is, ultimately you need an amplifier with high input resistance and low output resistance for better performance of the amplifier, cascaded amplifier stage. So which configuration will be ideal for this? Obviously this is a common collector configuration which has high input resistance and low output resistance, isn't it? But common collector amplifier has a low voltage gain which is less than unity. Therefore, this common collector is not widely used in amplifier circuits, but they are used in applications where requirement of high input resistance is of primary importance. Okay, now we'll see common base and common emitter. Which one we can use? The common base configuration is not at all recommended for amplifier. Why? Because it offers voltage gain, but it does not offer current gain. So it is used in pre-amplifier circuits. It has very low input resistance and very high output resistance, which is just the opposite of what we require. That is, what we require is a high input resistance and low output resistance for these amplifier stages. So we are avoiding common base also. Then what about common emitter? This is much better because its input and output resistances are about 1 kilo ohm and 10 kilo ohm respectively, which is in the medium range. Okay, so this range is considered to be better when compared to common base configuration. So the transistor in common emitter configuration will make a better amplifier. That is why we are widely using this common emitter amplifier in this amplifier circuits. So with this I am stopping the first lecture, and in the upcoming lecture we shall discuss this common emitter amplifier in detail. So thank you.